Welcome back. It's the week of the 30th. This is our second week after spring break. We'll finish chapter 3 in this lesson. We'll be skipping one of the sections. Uh, if you haven't yet, do take a look at the announcements on Blackboard. Although by the time you're looking at this, I likely have already created a couple synchronous meetings during the week. The goal is to have you watch these videos and try the questions first, and to treat those two sessions as recitations. This is an abstract chapter. Try not to feel too bad if you're struggling. I know it's compounded by distance learning, but this is the part of the course where people always do struggle. Let's just jump into it. So we've been talking about vector spaces, which are really abstract. We've abstracted the notion of vectors from pointy little arrows to anything that's in a collection that satisfies those properties. So sine and cosine are vectors. Matrices are vectors. Little pointy things are vectors. Lots of different things are vectors because they satisfy those properties. So we're moving into functions between vector spaces. So at some point when you studied functions, you studied the domain of a function, the range of a function, right? A function takes an input and it gives a unique output for that input, right? Functions only give one answer per input, all that kind of stuff. And so we're kind of revisiting that with the concept of linear transformations. But now we're between vector spaces. And if you took Calc 3, you actually talked about these things without knowing that you talked about them, because two-dimensional spaces R2, those are vector spaces. And so a vector field is a vector space. To every point in the plane, it assigns a vector. Anything that maps the line into 3-space or 3-space into the line and so on and so forth, those are all essentially transformations. Not necessarily linear, though. Linear transformations are a special type of transformation. So why do these have a different name? Why are they called linear transformations and not just functions? It's ultimately history, which was bound up a lot more with geometry. And so thinking about vectors, thinking about geometry, and thinking about what these transformations do. They often do things like scaling, reflecting, rotating. So we can think of them as geometric transformations. We're not going to, not very much in this class, but that's sort of the origin of the language. All right, so the definition. Let V and U be vector spaces. And suppose M is a function mapping V to U, which we'll denote with this notation. This is standard math notation, where you have your function, a colon, and then the domain. The arrow tells you where it's going into the range. So we'll refer to M as a transformation. And we're particularly interested in linear transformations. Why? Well, d dt is a linear transformation, as we'll find out, and so is integration. And those are the sorts of things we're interested in differential equations. So a bit more notation and language. So the image of a vector, that's just what happens to the vector. So you have some linear transformation, it does something to a vector, and the result is the image of the vector under a particular transformation. This preposition under is used commonly. This is the preposition used. We say that the image of a vector under a transformation is denoted blah, 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 okay? You'll see this little symbol in the slides and notes and stuff. It looks like a funny little E, and it means belongs to. So I would read these three symbols. I would read it as V belongs to V, or little v belongs to V. Part of the difficulty in chapter 3 is the abstraction. What little v do I mean? I mean any vector in this vector space. Which vector space is this? It could literally be any vector space. It could be something extremely concrete or something completely unfamiliar. So the generality here does make it kind of hard to follow along. In any case, so transformations are functions. So a transformation is linear if these two properties are satisfied. So the first one just means you can factor out a constant. So if you're taking a vector times a constant, you can multiply the constant after you're done evaluating. So in the book, they refer to this as the transformation preserves scalar multiplication. And then the next property is that it preserves addition. So the linear transformation, a transformation is linear if it takes the sum and you can do the sum afterwards. So we could also say it commutes with the sum. So again, these are pretty vague, pretty general. Why is this linearity? Well, if you kind of think about it, just naively, if t was a squaring function or something, then you couldn't do this, right? If you square cv, you get c squared v squared, whatever that means. So you couldn't pull it out. If you were squaring w plus v, then that's not the same as w squared plus v squared. So the whole idea of linearity as being something to the first power is kind of still in this expression. Let's do an example. So I said earlier that d dt was a linear transformation. Oops, typo here. Between f, the book uses f consistently to be the space of smooth functions. Smooth meaning you can differentiate it an infinite number of times, which is most of the functions that we deal with: sines, cosines, logs, exponentials, etc. So here's the notation, right? d dt is a function, mapping f to f. Take a smooth function, differentiate it, get another smooth function. Let's check that this is a linear transformation. For any real number c and any function f in the function space, in the vector space, the derivative of a constant times a vector is a constant times the derivative. You learned this in Calc 1, right? So check, it works. For any two functions f and g, the derivative of a sum is the sum of derivatives. Check. So I've checked those two properties on the previous page by using something specific about the derivative. These are properties of the derivative. And those properties of the derivative are linearity. Integral is the same way, right? You know that you can have, if you have an integral of 2 times x squared or something, you can pull the 2 out. If you have the integral of a function plus a function, you can break that integral into 2 pieces. So integrals are also linear transformations from f to f. All right, so multiplication by a real number is itself a linear transformation. So, again, you go back up here. But actually, this would be a good one for you to check yourself, and you can ask me about it during our synchronous meeting. So multiplication by a real number is a linear transformation from f to f. Here's another one. Evaluation is a linear transformation. So let's define capital M on a function f as evaluating at 0. And let's suppose that f on R to be all those smooth functions defined on the entire real line. So I'm being specific here. So a function that's not in here is ln. Right? That way we don't run into problems with evaluating at 0. So then M maps f of R to, oh, this is a typo actually. Let me pause and fix this. All right, fixed it. Sorry about that. So M is a transformation that takes functions on the real line and it maps them to numbers. So here are some more abstractions. The real number line, the x-axis, if you will, is a vector space. Scalars are vectors. Yeah, I know this is somewhat earth-shattering. Scalars are vectors. You can check all the properties. So ordinary numbers are vectors themselves. Very, very weird. Anyway, so we can take functions and we can map it to numbers. We just map it to whatever the function equals when you plug in 0. So this is a transformation. Let's check that it's linear. So when checking these definitions, we're just choosing an arbitrary function f. We're not choosing something specific. We don't want to assume anything particular about sine or cosine or e to the t or whatever. So we take some f and we have some c. We say, well, what happens when we do this? Well, a number times a function evaluated at 0 is a number times a function evaluated at 0. But f of 0 is exactly the result of m on f. So this is kind of weird, right? We start off with something general here. We write what its result is. And notice I'm not worrying about what f of 0 is. Maybe it's 7. I don't know. It doesn't matter. And then I'm replacing f of 0 with m of f, which is exactly what was given in the problem. And the point of this is I have the left-hand side and the right-hand side demonstrate preservation of scalar multiplication. Right. It's a little weird. Second property, take m of f plus g, where you're allowed to add functions together. If you add functions together and you evaluate at 0, that's just the same as plugging in 0 to both functions. F of 0 plus g of 0 is the same as m on f plus m on g. So again, it's the same as before. I'm starting at the left-hand side, and I'm trying somehow to get over here using the properties that I know about. So then this is a linear transformation. These are weird. These are different. These are super important in terms of like later on partial differential equations and stuff like this. So the whole point of doing linear algebra in the context of differential equations is that differential equations makes more sense in the context of linear algebra, especially when you consider things like eigenvalue problems where you have vectors and transformations, but for other reasons too. All right, we're going to pause here for practice, and I'll see you in a minute.